going to close out our morning main stage for today with our speaker, Brad Settlemeyer of Los Alamos National Labs. I had the opportunity to hear Brad speak at Flash Memory Summit a few weeks ago in the persistent memory track. He's a senior scientist at Los Alamos National Labs HPC Design Group, where he leads the storage system research efforts within Los Alamos' Ultrascale Research Center. Today he's going to speak on a very important topic to all of us, high-performance computing and artificial intelligence and designing storage systems with them. Welcome, Brad.
Thank you. So I am Brad Settlemeyer, and this work couldn't have been done just by me. There's obviously a lot of people that were involved, and I real quickly just want to make sure I at least put their names on the screen, and you can call all of them and ask them about all the great work they did here. I want to try and cover three things in this talk. A real quick, like 6-minute maybe, discussion of what simulation science is, HPC storage systems, how we construct them. Then I want to real quickly introduce DeltaFS, talk about designing a data plane for a metadata monster, how we got from millions of file creations per second to billions of file creations per second. And then finally, I want to move beyond DeltaFS and talk about converging storage for HPC and AI. So I always like to draw a picture of an example of an HPC platform. So what you can see on the left-hand side is the gray compute nodes that's connected by some kind of network. Here I've just drawn it with a very simple little 2D torus. But that's where the compute jobs run. And so the compute jobs run in such a way that you're running across, say, 1,000, 2,000, 3,000 nodes, 128,000, 256,000 cores. And you're going to run for some amount of time, and you're sending messages all the time to try and collaborate on this calculation. You're doing some big distributed DGEM, some big distributed sparse array. And then you got to pause the simulation. And you're going to pause it, and you're going to take all the memory state, not all, but 25 to 75%, and you're going to jam it down into the storage system. And you do this for reliability, but you're also going to do this for later analysis. And so this is kind of the critical thing to understand about the HPC workflows, that we're going to compute for some amount of time, but when we're running across thousands of processor or thousands of nodes, hundreds of thousands of cores, we're going to take errors. We expect about once every 24 hours on a system like Trinity, we're going to take an error. And so you can see that we've got to get that data either to the edge, where we have some storage on the edge of the platform, what we call burst buffer nodes, or through a set of routers that are going to take us out to a parallel file system. So this is effectively what you get on something like Trinity. You're going to have a tightly coupled parallel application, and then suddenly you're going to stop, you're going to quiesce the network, and you're going to have to dump all of memory as quickly as possible into some kind of fast storage tier. And so within the Trinity system, we have 19,000 nodes. We have two different types of processors. We have Haswells and we have KNLs. So on the order of 1 million cores. And you have a burst buffer that's about 3.7 petabytes, 3.3 terabytes per second. The file system we run on the burst buffer is the Cray data warp file system. Talk very briefly about that. It's a slightly relaxed POSIX consistency file system. Below that, we also have a Lustre parallel file system. It's actually split into 2 file systems so that we can service it correctly. So it's 2 596 gigabyte per second file systems. Each one's about 35 petabytes approximately. And then below that, we have a longer-term storage tier. And so one way to think about this is the burst buffer, you've got 4, 6, 8, maybe 24 hours of storage. Within the Lustre file system, maybe you're talking about 12 weeks, 16 weeks of storage that you can leave your data there and not feel like you're eventually going to be under pressure or some admin's going to tell you to get your data off the file system. And then down in the campaign tier, which is much slower, it's a mix of shingled disks or it's tapes. You're going to see that you can leave data for months as you need. And that's important because our jobs may run, I think the largest simulation that I'm aware of that we've done was across approximately 4,000 nodes for about 7 months. And so there was a lot of faults, there was a lot of state, dumped a whole lot of 35 terabyte state files, created hundreds of terabytes of analysis data. And that's kind of the basic workflow. So I just wanted to make sure we all had that background. So what is the problem with our current file system structure? So we use parallel file systems. This is kind of they aren't a descendant of distributed file systems. Instead, they're kind of like a sibling. They both started in about the same time, I guess. Our current parallel file systems were kind of started from an effort in about 1999. We run a lot of Lustre, but GPFS has a similar type of file system and has a similar history. PFSs are great whenever it comes to assembling a whole ton of peak storage performance. If you want to get a bunch of petabytes together and several terabytes per second of capacity, or terabytes per second of bandwidth, PFS are great. They have fixed layouts, so you can get all your spindles active, you can get all your SSDs active, you can get a really wide stripe, and you can get a whole lot of material pushing bytes at the exact same time. Really prefer very large requests. We're tuned up for large requests. We're trying to do this bulk synchronous. Our applications are not as great at it as we would like. We're under intense memory pressure on the applications. They're using 70, 80, 90% of memory. So we don't have that ability necessarily to build big buffering layers, but we do try to do some shaping on the I/O. So we will have something, but for our big application, we get a mix of like 12 megabyte requests whenever the buffering is going well, but 32K requests whenever things are going poorly. And again, you're dumping it out as quickly as possible, so you don't necessarily get as much time to shape the I/O. You want to have that storage active at all times. These file systems tend to relax consistency slightly, and this turns out to be perfectly fine. Data warp is what you would actually call like a byte level coherence is the consistency scheme. It's not quite as bad as like closed to open, but as long as you don't write in overlapping regions, you get a pretty manageable consistency semantic. And we always prioritize write performance over read performance. We are the kings of write once, read never. The goal is to not have a failure and never need that checkpoint. And then you can shrink your analysis data, and maybe you can only look at the last one of those if that's all you care about is get one number at the end. Our problems are, what about other I/O types? So namespace mutations and accesses generally don't scale well with hardware. Whenever you look at our metadata servers, we're not bound by the devices that are on it. It doesn't matter what device you put on. A lot of what we're bound on is how fast we can spin inside of locks, how fast we can get access through some directory where we've got to spin through some kernel infrastructure. File create performance within a single directory is particularly bad. And poor support for these small requests, anything less than a few K. What we're going to talk about today is 48 byte requests for DeltaFS. Those are particularly challenging. We're not a great IOPS workshop. And then just real quickly talk about them. Compared to the modern DFS, we're not anywhere near as good at like adding storage. These are not scale out. These are forklift upgrades. You drop it on the floor, you put all your storage on it on day one, and that's pretty much all you can do. It took 7 minutes. Okay, so quickly moving on to DeltaFS. I want to give a quick review of DeltaFS, or maybe a little bit longer review of DeltaFS. So DeltaFS is a project we did with Carnegie Mellon, Lionel and Carnegie Mellon. And the lead grad student is here, and I'll talk a little bit about what he's going to talk about a little bit later. But DeltaFS was designed to be a scalable metadata plane for HPC clusters. And so it's built on a few tenets. It's got scalable metadata performance. It actually didn't even have a plan to have a data plane. The whole idea was maybe you'd run it on top of something like Rados or some object storage system. But then as we tried to push into these absurd numbers like 1 trillion files, it became necessary to put a type of data plane on it. You're not going to write terabyte-sized trillion files. Or at least we're not. And so it's got log-structured metadata. It's a no ground truth namespace. I'm not going to describe much about that today. Although Ching will later. Accelerates file creation in a single directory. I'm going to talk a lot about that. In particular, the technique called an indexed massive directory, and that's how we can get this massive create rates. But we're also going to talk about how we're going to accelerate small writes. I've heard it called the dribble write problem. We're going to be writing out data 48 bytes at a time. And then I want to show an example of how we accelerated a science workflow. Okay, so we're going to go back to our picture of a platform. And this is kind of giving you a little bit better idea. So you can see that we have a lake of compute nodes out to the left, and then we have a storage system far out on the right, and then we have like a burst buffer maybe on top with the dark blue, and we have the gateway nodes that can bridge the networks, bridge between the two network types, some kind of high performance interconnect on the left, and some kind of high bandwidth InfiniBand connection on the right. And what you can see is that we have dedicated file system servers in this case. And I drew 3 purple boxes, dark purple boxes at the top to kind of show the metadata service. And this is one of the problems we have. So we can create a metadata service. Maybe we can do a little bit of DNE2 or DNE1, and we can get a few metadata servers. Maybe we can get 6 or 10 metadata servers, and it'll scale kind of somewhat okay. But it really constrains how we're going to design that platform on the left. If the deal is I want every single core, and I've got, say, 10 million cores to create a file in 10 seconds, well, I have to provision that metadata service for that system design. And so it really constrains what I can do in system design. I can't have 50,000 nodes, which is what Aurora was talking about and why they're looking at systems like Deos. I just can't get a create rate, a metadata rate that can actually do that. So the file system is unfortunately going to constrain our ability to design a system within some degree. We can't get the kind of create rates. And I can buy $75,000, $100,000 metadata servers, but I still can't really get them to perform at those rates. I mean, what I'm really buying is, platinum processors that are quite expensive, just trying to get a little bit more churn. What I'd really need is a 10 gigahertz processor to get more performance out of my metadata service. And so the key idea with DeltaFS is client-funded metadata. So how do we push the metadata work? We've got all these great servers out here in this lake of compute. They're perfectly good servers. They've got perfectly good processors. Why can't we do the metadata out there? And so this is the first key idea of DeltaFS. Transient DeltaFS servers that you can stand up on demand and establish a namespace, scalable namespace as you need. Here I'm showing that there's actually, you don't just have to do 12 or 15. In our case, we're actually going to do 4,000 metadata servers whenever I show you the trillion creates, 128,000 total servers. Even 256,000 servers, I guess, in the very biggest examples we did. And so you have to change a lot of things to do this. You're going to change the namespace semantics. You heard the talk earlier about relaxing the data semantic. And the way you accomplish this is you relax the namespace semantic quite a bit. So we're going to eliminate provisioning dedicated metadata services for peak bursty. We're instead just going to have a metadata service that's dedicated to address all the objects in our file system. We're not going to worry about its performance. And we're going to stand up DeltaFS servers to meet our performance demands. So we're going to need some way of doing some kind of bulk metadata operation. We do this by using an LSM tree organization for metadata inside the transient server, so it all get logged. This builds upon the lessons learned in TableFS and IndexFS. And this really suits HPC workflows where we can actually co-locate metadata with the application pretty easily. Again, we're going to quiesce the network. We get to reuse all of those resources while the application's sitting there doing idle. As long as we don't use any RAM, we're okay. We can borrow the cycles. So we've got to keep the memory image quite small. And the easiest analog to think of it is it's kind of a Git model for file system namespaces. You're going to check out a version of the namespace, modify the namespace locally, then do some big bulk insert back into some notion of a global namespace. And of course, the problem is you have to handle conflicts. And not to steal what Ching's going to describe earlier, he's going to describe all the caveats that come with this in a talk at 1 p.m. But the answer is we don't handle conflicts. We only resolve them whenever we have to. We want to be real lazy in how we do that, because having a strongly consistent namespace is going to go much slower. And so this will get you some really great performance. I mean, DeltaFS can absolutely rock and roll for creating files. So if we look at what Lustre can do, maybe you can get 100,000 creates. Maybe that can be pushed up to creates per second. Maybe that can be pushed up a little bit higher if you work hard at it. DeltaFS is going to drive you right into the millions pretty easily. You stand up a bunch of servers. But what if we want to do billions of files per second? How are we going to do that? And so that's what the remainder of, or that's what the second part of this talk is now. And so we're going to use something called an indexed massive directory. And this is DeltaFS key idea number 2. But in order to start talking about this, I want to real quickly talk about the application that motivated it. I mean, why would anybody really need a trillion files? It's kind of an absurd thing to talk about. So this in the background is a VPIC simulation. What's happening is a charge-neutral plasma is being formed. So we have a bunch of electrons and a bunch of positively charged ions, effectively positrons, and they are sliding across each other to create a plasma in space. This is the kind of thing that we simulate at Los Alamos. We're interested in plasmas. This is an astrophysics thing that can happen out in space when you're creating a sun, I guess, or something. So what you'll see is you'll have these magnetic reconnections, and we have these things called magnetic islands. And each one of these colors here is actually a particle. These are massless particles that we're showing, and this is on the order of trillions of particles that you can see because you've got quite high resolution in this picture. And so VPIC is the vector particle and cell code that we use at Los Alamos. Super efficient, runs across thousands of processes easily, hundreds of thousands of processes easily, scales like mad. Very efficient computation infrastructure. And so effectively what you do is you take space and you subdivide it into a mesh, exactly like you would think. In this case, it's a fixed grid, super easy. The particles are 48 bytes. They have a momentum and a position, and that's really about it. And on each process, we're going to have about 2 million particles. We've also got a set of fields that are associated with the grids. The end result is we've got about 10% of the memory left. VPIC and the OS require about 90% of the memory on the nodes. And the scientist wanted to do 1 trillion particles. And in particular, what he wanted to see was which of the particles would take a high energy excursion off into, or a high energy excursion. And what they do is they'll vibrate between 2 magnetic islands. At least this was his hypothesis. It's been known for a long time they'll vibrate due to collisionless shocks. But he had this theory that they would vibrate due to connections between magnetic islands and take off into this high energy regime. And so the problem is, you're under intense memory pressure to store the current state of the particles. You have no hope of storing the history of the particles. And you don't know which particles are going to vibrate and enter a high energy regime. In fact, you don't even know that this really happens yet. So he wants to look at this and determine this. And so the way you would do this in a traditional system, so if you took DeltaFS and you combined it with just some kind of regular backing store, is you're going to create a file at every process. You're going to create a log, and then basically you're going to take a 4 megabyte buffer, accumulate 48 byte particles, and then fill the log. Just do appends into the log 4 megas at a time, get fantastic rates. So it's a really great I/O pattern for shoving the data out the pipe as fast as possible. And there's about 40,000 time steps, and about every 500 time steps is enough resolution to catch the vibration. So you can, the time step here is on the order of a nanosecond or something. And you're discretized in time, capturing the position of all the particles. So this is a great figure. So if you look at particle A, which is in the first time step, it's in the left-hand process, and then later, particle A with the little red line behind it is in the second process. This is because the processes are, of course, moving at relativistic speeds. They're moving all through the mesh. They're reformatting. They're vibrating at best between these magnetic islands, if our scientist is correct. Then the only way to actually access this data is to either, once I've written out all these terabytes of particles, is at the end of the simulation either do an exhaustive search or sort all the particle logs, depending on how many particles you actually want to retrieve. Those are basically the 2 ways of doing it. Either way, you're going to take Trinity, you're going to reuse all the memory to do some big tera sort or some big tera search. Those are kind of the 2 ways to do it. And the key idea is that we can't figure out what the interesting particles are at the beginning. We want to just go find the ones that had high energy and then look back in time and see if they actually vibrated back and forth. So our great idea was, well, wouldn't it be a whole lot better if we could actually just do a particle per file, and at the end of the simulation, you say, well, I care about these 10,000 particles, they have high energy, and rather than sorting some big log, can I not just go, okay, I'm going to open file A and read its history, then I'll open file Y and read its history, and I'll just read back through the history of the particles. I'll effectively use the file system to index all the data. So suddenly we've gone from creating hundreds of thousands, possibly millions of files, to now we want to create 1 trillion files all in one directory. We want every particle in a file. So how are we going to do this? So here are kind of the 3 candidate approaches. So the first approach is the traditional approach we talked about, where we're actually going to do a big post-processing step. We're going to need about 1 terabyte of RAM at the end to search through all of those particle logs. The second one is we could kind of do the same thing. We could create a file system that could create 1 trillion particles, but we still have to solve that problem for writing out 48 byte writes. So every time I do an F write on 48 bytes, I've got to figure out how I'm going to get that data buffered up. We're not going to do 1 trillion 48 byte transactions and it finish in our lifetime. It's just going to be too much. Even if it's SSD, it's just too small. Network costs, you get crushed. And so we could have this notion of somehow we took dedicated servers and set them up as an indexing pipeline so that we could fill this data into a big container that's indexed correctly. And we could have these dedicated servers that would buffer up each of these files. We could do a technique like partition file domains, have nice big 4 megabyte buffers for something on the order of 1 trillion particles. Well, we're starting to talk about a lot of RAM here, just as much RAM as the simulation has. Maybe not quite that bad. But we're going to have dedicated servers, and that's just antithetical to the idea of DeltaFS. We don't like dedicated servers. We want to do everything as this transient service that you can stand up and tear down on demand. So that's the last approach on the right. So how are we going to take DeltaFS? We're going to tag all this data as it goes into the index massive directory so that we can pull it out a file at a time. And so somehow we're going to do this, and we're going to do it just using 3% of RAM, because we don't have enough RAM inside to do a whole lot of buffering. So somehow we're going to get all this performance out of this system by only using 3% of RAM to shove 48-byte particles into much bigger logs. Obviously, we can't write out 48-byte particles. So this is a DeltaFS index massive directory. So on the right-hand side, you can see kind of the logical idea of the concept. So again, we have all these processes. They've all got just a random collection of particles on them. And the very first step we're going to do is we're going to shuffle all the particles to a home location. So every particle has a home. We're going to use a hash function. A partitioning function is the way to think about it. So now we're going to have, again, in the largest case, we've got 256,000 processes, so 256,000 partitions. We're going to run with 200. Directory is going to be composed of this 256,000 partition deep, where we can actually just immediately hash to figure out where this file is, and we can immediately cut the space down by at least 256,000 times. Then inside of there, we're now going to figure out how we're going to accumulate the particles into some kind of buffer so that we can write those in. We're again going to take the same idea that we used for metadata. Metadata is a very similar problem. It's small updates. So now we're going to actually log the data with the actual file name. So we're going to actually expose kind of a log structured merge tree. Except we're not going to do compaction, because compaction would again crush us. So in this case, we're just going to write the data out into hash tables. And so what you can see at the bottom is that if this all works correctly, what we're going to have is we're going to have an index for each of these partitions so that we can rapidly go search files out of it. And rather than searching terabytes of data, we should just be able to go pull back a megabyte of data to read the index and then immediately go dead reckon for our particle trajectory. So the implementation is shown kind of up here in the upper right. And so what you can see is that there's a big shuffle pipeline, and this is based on the Mercury RPC package. It's actually one of the technologies that underlies Deos that she was describing in the last talk. They use Mercury RPC as well. It's a highly efficient RPC package. It takes advantage of our low latency networks. Even so, we're still going to have to package things up into 64K buffers in order to drive the network in the bandwidth regime rather than in the latency regime. I'm not going to have time to talk about how we did all that, unfortunately, but we effectively implemented a software dragonfly routing scheme inside of this shuffle layer. Then once you enter the delivery queue, now you're going to get the buffering so that you can actually buffer this up. You're going to buffer up particles randomly, and we're just going to use an LSM tree. So we're going to fill a mem table with key value pairs of particle ID and trajectory, and then we're going to spill those to disk. But rather than spilling them to disk as SS tables, we're going to spill them as hash tables, but they're really kind of approximate hash tables. There's no point to do a full compaction or even a full sort here. Instead, what we're going to do is we're going to create a filter block for a mem table, a index block which describes where within the data block, because again, lots of 48-byte particles, where within the data block to look, and then we're going to be able to cluster that entire index, as you can see down at the bottom, so all the filter blocks and index blocks, we can retrieve those for a single partition. Now, one of the things I talked about a little bit earlier is maybe there's more than one partition per server. And this is because we can't actually calculate the filter blocks, the index blocks, and spill to disk and keep the disk busy all the time. This is one of the key ideas within DeltaFS, is you've got to be bound on the disk. That's the slowest piece. You have to be pushing to the disk at all times. And so, in fact, we have to have 4 mem tables active at any particular time so that we can make sure we've always got something that's spilling to disk. The calculations aren't intensive to calculate a filter and index block, but even so, we really need no pipeline, or no pipeline gaps to be able to get the maximum performance. And so this is how it worked. So on the left-hand side, you can see the overhead. We're writing out more data. It's about 3 to 5% more data for those index blocks. So effectively, we've turned a directory into a set of silos of partitions, quite a few partitions, 4 times however many servers we have. Number of processes, which is also the number of clients, and the number of servers is along the bottom. So you can see once we get out of the regime where we've got the startup, the light blue line is showing that the performance is fixed for the baseline case. And this is because we're holding the number of burst buffer nodes fixed to make this much simpler to think about. We're going to maintain a 32-to-1 compute node to storage node ratio. So we're going to write into that file system at 32-to-1. So you can see that, in fact, the baseline performance is fantastic. It really can shove a file system full. And DeltaFS is a little bit worse. We're about 8% slower, which we're only about the data is only about 3% larger, so you can tell that the shuffle comes with some cost. The shuffle isn't free. There's a lot of work. And then as we get out, you can see that the shuffle algorithm starts to really run out of steam at really large scales at 128,000 cores. We're up at 35% slowdown. It's not too bad whenever you look at what comes next, but it does cost a little something to shuffle the data, in particular as you get as the ratio of bisection bandwidth increases. We're using a lot of the network at this point at 128,000 cores. That's 4,000 nodes at that point. So the right-hand side shows how long a query takes. And I can't really scale the queries all the way out because it would be irresponsible to run the baseline at much larger than this on a government resource. So it's about 10 minutes in the largest case to do the query in the baseline case. It's about 543 seconds. Whereas you can see that the DeltaFS, where you read in the clustered block, is always less than a second. And in fact, if we took it out to 128,000, you would see that DeltaFS would be about a half a second to actually retrieve a trajectory. So you can retrieve, I don't know, 10,000 trajectories in about an hour here, whereas it would take on the order of 6 months to retrieve 10,000 trajectories. And as part of this, we created 1 trillion files. And I don't know that there's a world record for this, so I didn't write the headline on the world record part. But I don't think many people have created 1 trillion files in about 2 minutes. So it was a pretty stunning create rate. And the key takeaway that I want to talk about here is it's really only possible because of the techniques from key value storage. By blending those with the file system and creating a directory container that is effectively a key value store, where we're logging all the metadata and logging all the data, we're able to get these incredible rates. So now this leads to the final part of the talk that I wanted to get to. And we're actually here with enough time that I can talk about it. And so beyond DeltaFS, trying to look for converged data models for AI and science. And so this is one of the things that we're really interested in. And the kind of the lessons from the indexed massive directory really drive this analysis that I'm getting ready to talk about. So this is an example of a different kind of simulation. This is called an adaptive mesh refinement technique. This is an AMR mesh. Having mesh in there twice is a little weird. And what you can see is it looks like there's like these little pillars kind of in a fluid, like it's in an aquarium, and the water is kind of moving and it's swirling around. And what you can see if you look at the refined area is that as there's more turbulence, the mesh cells are going to be smaller. And we do this for memory saving, right? If there's no energy or there's nothing happening in a cell, we want to take up as much space as possible and not have to waste any memory storing the state of that cell. And so if I were to run this simulation as a movie, which after watching the awesome talk earlier, I should put movies in. But you would see it refining and de-refining as those turbulence twists around those pylons in a liquid. And so the question I always ask whenever I look at this mesh is, well, how many rows are in each of these columns? And it's of course a trick question. It's different, right? And you can even ask it in the more funny, which is how many of these columns are in each of these columns. And what you can see is that it's an unstructured mesh. There's no way to make sense out of this. And so whenever I try and map this to a one-dimensional array of bytes, or a file as we know it, there's really no reasonable way to do it. I mean, you can do something silly where you try and space out and have big sparse files and you do some mapping, but depending on the levels of refinement, it gets crazy on you. And the answer is what people do is they actually store it in a bunch of files. So what they do is they take each of these levels and they store the largest level in a file, and they call that the level 0 file, no relation to LSM trees. And then there'll be level 1 for each of the refinement levels. And usually there's a limit on how much the simulation package will allow you to refine space. So maybe you can go up to 16 levels or something like that. And there's a bunch of constraints about how much you're allowed to refine around some area that the simulation will be enforcing. And so what you'll find is that the first file you can store in some order. You can do it in maybe row major or column major order or a Z order, which is a space filling curve. And I'll show an example of that a little bit later. But when you start talking about the other layers, or the other levels, effectively the data is randomly refined. I mean, you're simulating it because you don't know what's going to happen. You're under memory pressure. You can't sort all the cells. And so effectively what you have to do is you have to shove each of the levels down with their metadata describing their exact location. So you end up just having to write the data out in random order after the first level. And And this is a problem with mapping down to a one-dimensional array of bytes. So you remember me talking about the key value. So one of the things that we always try and look at is, well, what are other people doing? So we went through and we did a quick analysis of, I'm in the furthest left-hand corner. I'm simulation science. So we looked at other sciences, and we just look at the number of keys. We've got 1 trillion keys for 1 trillion mesh cells. The molecular dynamics and the bio guys, maybe they've got 1 billion base pairs, maybe 1 billion atoms at the absolute outside. The AI people have maybe 1 million parameters in their parameter space. They do have trillions of training files, but that's big bulk data. It's not exactly representative of what you'd see in a mesh. And the graph analytics guys are kind of similar. They had 100 billion nodes or edges in their graphs, and so maybe there was some issues that we could borrow. But then you look at what they do, and it's a read-intensive workload. But then recently, a great thing happened. The AI folks started doing outrageously large neural networks, these ensemble mixture of experts methods. And I am by no means an expert in AI, but I am super excited by this idea, because finally we're lined up. Simulation science with our trillions of keys, AI with their trillions of parameters. Our values are maybe a little bit larger, but it's very, very similar, and it seems like we finally got a chance to converge with those guys. So if you look at the different operations that we have here, so as we're a throughput write shop, so we're going to take all our keys and we're going to use techniques like index massive directories to bundle those up. We won't always be as bad as 48 bytes. In general, we'll have maybe 10, 12, 14 doubles. That'll be our kind of what's in a cell. Maybe 50 doubles at the outside. So we're going to need that ability to do bulk inserts. We love range queries. We want to be able to track where those phenomenons, where that wave is moving through space or through the aquarium. Also interested in point queries if we want to do particle analysis. Other sciences are kind of similar. They're going to do maybe more point updates, maybe more point queries. And in the case of bio, maybe a lot of mmap, which is a little bit hard to figure out exactly how to map that in as a key value work. Might be possible. The mmap semantic is so strange. But you look at the AI people again, and here we are. So now, it used to be the case you'd say, well, all they're going to do is they're going to read a parameter, recalculate a new weight, and dump it back on. But then you look at projects like PipeDream and Boson, and they're all going into this model where they try and relax the stochastic descent as much as possible, and they want to batch up these updates. This looks exactly like HPC again. So here we are, where we can see a chance to converge in how they're doing their updates. They're looking at how to do a more efficient update on these massive models. The training data is, again, bulk retrieval. I don't know exactly what to do about that yet. And then, again, we have these point updates, or these point reads at least, with the graph analytics workload, where they're trying to maybe they're calculating new weights for the edges, or maybe they're doing pointer chasing through some massive graph to find relationships, and you bought this, you would like to buy this instead. And so we can see that there's a lot of similarity in the workload. And what we can also see is that while HPC is currently a decent amount larger in how large we run our jobs, it's certainly true that the analytics that you see from something like Microsoft Cosmos, where they have these massive 50,000 node clusters, far, far larger than Trinity, our biggest system, that they've got this capability to run massive graph analytics. They just maybe haven't told me about it, which is fine. They don't have to tell me anything. And we're starting to see, I think, with these outrageously large neural networks, maybe that we don't know exactly what the largest training processes are, but I suspect there's been trainings that are on the order of 10,000 nodes. But for sure, they've done trainings at 1,000 nodes. And so the only real problem we have is maybe there's a little bit of difference in what the values are in a key value store. That we're 10, 12 doubles maybe, whereas when you look at what the AI workload is, they're trying to shrink the precision down. They're down to 8, 6-bit weights or something like that. That's a little bit of a difference, but we're still very, very small. We're still way under a block in both cases, so way less than 4K. And if you look at graph analytics, those guys have the worst of it all. They're always a pointer. They're always chasing a pointer, updating a weight. And so what I think we want to look at is prying open the index massive directory, not even putting the fwrite shim over top of it, and instead just exposing the key value to the application and very easily building very thin shims that can turn a parameter server for an AI workload into a mesh server for an HPC workload. These are the same data structures that we've always been using in file systems. It's B trees, log structured merge trees. These are all key value stores effectively. It's just different ways of iterating along the bottom of the B tree, the nodes at the bottom. But rather than hiding it under a file system interface, we need to actually bring this interface directly into the application. I think that ROX and LevelDB have all demonstrated that this is an application interface that's useful for applications, and it's a chance for us to build a big distributed key value store that really suits all of us. So for HPC, we're going to need a little bit of HPC research. We need to use our low latency networks. We're pretty tied to that. It's important that we're able to leverage those. But we also have these indexed massive directories. But we also get this one huge gain. So I talked about how it's difficult to map a mesh space onto a closed one-dimensional byte. But a key space isn't one-dimensional. A key space is an open range. So you can actually keep refining the key. And so we just borrowed the technique from the Farsight file system that Microsoft prototyped a few years ago. And we just used dots to separate the levels of refinement. And we can just tack it all in there and iterate over it in order. It's super easy. And so this is already a huge gain in simplicity for how we can begin to look at our meshes. And so this is an appeal to do a converged system software for AI, HPC, and analytics. Let's get some of the building blocks together. I don't know whether it's indexed massive directories to act as containers, a hierarchical way of accessing key value stores, relaxing the namespace consistency is something that DeltaFS has pushed a great deal. There's non-POSIX consistency models. Those are already pretty common. So it seems like we have the chance to do this and build storage systems that can converge all of these different workloads and maybe allow you to tune the trade-offs that you make all through the same key value interface. So to summarize everything that I talked about, brief overview of HPC platforms and simulation science. You can read a whole lot more about that in an article we had in Login magazine. A brief overview of DeltaFS. This is the paper that introduced DeltaFS and its scalable namespace. And Ching will talk a lot more about that at 1 if you want to hear a whole lot of gory details about how to relax namespace consistency. Indexed massive directory overview a couple years later, and how we scaled it up to 1 trillion files last year at SC. And then finally, the kind of stuff that I'm reading, trying to learn about ensemble learning models, outrageously large neural networks. Thank you.